Euclid's Elements, Book 3, Prop 8. If a point be taken outside a circle and from the point straight lines be drawn through to the circle, one of which is through the center and the others be drawn at random, then of the straight lines that are drawn through and that fall on the concave circumference, that through the center is the greatest, while of the rest, the nearer to that through the center is always greater than the more remote. But of the straight lines falling on the convex circumference, that between the point and the diameter is least, while of the rest, the nearer to the least is always less than the more remote. Finally, only two equal straight lines will fall on the circle from the point, one on each side of the least. So this is a massive enunciation, but basically if we take a point outside the circle and from that point lines be drawn through the circle, one of which goes through the center. So let's have the center of the circle be here. So here's our points. So we have a line going through the center, and then from here we just run this at random to various parts of the circle. So let's call this point D, we'll call this A. We'll call the center of the circle, we'll get to it there, so we'll call this B here. And then these we'll call, we'll call this E, F, and G, and then we'll call this K, J, and L. So here's what we're going to say, three different things we're going to prove. The first we're going to prove is that DA, line DA is greater than DE, which is greater than DF, which is greater than DG. So the line through the center is the longest, and as we get more remote, the lines get shorter. But that's on the concave side, but on the convex side, the opposite. This will be the least great, and then these will get longer. So the second thing we'll prove is that DB is less than DK, which is less than DJ, which is less than DL. And the third thing we'll prove, and we'll hold on to that for a second, is that from this point, only one equal straight line will, two equal straight lines will fall. So if we take this line DK, only one other line will be equal to DK to the concave part of the circle, and it will lie on the other side of this least line. So we'll hold off to that. So we'll say that DK, there's only one line equal to DK. So let's start with the first part. The first thing we want to do is we want to take the center of the circle. So let it be M. And so we're going to start by proving this first series of things. And we know that, let's connect this here. So we'll connect EM. We know that MA and ME are equal because they are radii of the same circle. So MA equals ME. And so we can add MD to both. If we add MD to both sides, so we have MAMD, which is simply DA, is equal to MEMD. But MEMD are simply the two legs of this triangle DEM. And we know that any two legs are greater than the third leg, according to Book 1, Prop 20. So EMMD, these have to be greater than DE. But if DA is equal to these, then DA is likewise greater than DE. So DA is greater than DE. And that's the first thing that we prove. Now the second thing we'll prove is, connect EM here, and now let's look at the two triangles. Triangle DEM, I'll call this the green triangle, and triangle DFM, call this the blue triangle. And what we see is that both triangles have a radius in common. EM equals, so we know that EM equals FM. And we know they both have this MD in common, so MD is common. So we have two triangles that have two legs equal to two legs. So this triangle has these two legs that are equal, and this triangle has these two legs that are equal. The only difference is the size of the angle. As we can see, the size of the angle for the blue triangle is this, but the size of the angle for the green triangle is this. It's bigger. And we know that in that situation, the side subtending the greater angle will be the greater side. Therefore, DE, the side subtending the greater angle, has to be greater than DF. And that is the second thing that we're trying to prove, which we have done. And we can use that exact same reasoning to show, so in this case, we're going to get rid of this, and now we're going to look at the blue triangle, DFM, and what I'll call the purple triangle, or plum triangle here, DGM. And we can see the same thing. They have two legs equal to two legs, but the angle of the blue triangle is bigger, therefore DF is greater than DG. And that is, of course, the third thing. So we've now proven that this line is greatest, and as we move further away, these lines get progressively smaller. But when we look at the convex, so this is the concave. On the convex side, we're going to see the opposite. We're going to see that DB is going to be the smallest, and these other lines are going to get longer. So I'm going to take off some of these unnecessary lines, and now let's look at this triangle here. So we have triangle DKM, and we know that MK in this triangle, MK and KD, they are two sides of a triangle, and therefore they have to be longer than DM. This is prop 20 again. Oh, by the way, these props that we used here are prop 24, book 1. All right, back to this triangle. We know that these two sides are greater than this side, but this side, DM, is simply made up of DB and MB. And we know MB and MK are radii of the same circle, therefore they're equal. So we can remove those two equal portions. So if we take MK out and we take MB out, because they're equal, the inequality that remains, we have KD is greater than DB. Or conversely, DB is less than DK, which is this first part. Now let's look at another triangle. So let's connect here. And what we have now, we want to look at a triangle DJM and triangle DKM. And what we see is that they're on the same base, but this triangle DKM is inside the larger triangle. So we have a triangle like this. We have one triangle like this, and we have another triangle inside of it. And what we know from, and this is prop 21 of book 1, we know that this smaller triangle will contain a larger angle, but the sides will be less. So we know that the sides, so let's look here, we know that side DK and MK are less than the sides DJ, JM. But of those, we know that these two are equal. We know that JM and KM are equal. So we can remove those, and therefore the parts that remain, the inequality still remains. Therefore, the remainder, DK, is less than the remainder DJ. So DK is less than DJ. And that is this portion. And we can do the exact same proof for this triangle here. So again, we have this triangle, DLM, and triangle DKM is on the same base but meets inside. Therefore, these two lines are greater than these two lines. but these two are equal. Therefore, when we remove that, the remainder is greater than that. Therefore, dj is less than dl. So that's the third thing that we prove. Second thing. Now, we say that from this point, there's only two equal lines that fall from that point to the circle. So if we consider a point, say, dk, there's only one other line that will be equal to it. So let's construct that line. The first thing we're going to do is we're going to take this angle here. So this is our third thing that we're doing. And we're going to take angle KMD. So angle KMD. We're going to construct another angle equal to it right here. So we're going to make angle DMB equal to it. And then we're going to connect these points. And so let's call this, N. So now we look at this, we look at these two triangles. Look at triangle DKM and triangle DNM. And we notice here that they have an angle equal to an angle. And these are both radii of the same circle, so those are equal. And then they have this side DM in common. So we have side, angle, side, side, angle, side. So we can prove that these triangles are equal. So triangle DKM is equal to triangle DBM. And this is prop 4, our side, angle, side proof. And that means all the triangles are equal in all respects, particularly here that this third side is equal to this third side. So DK is equal to BN. I'm sorry, DN. DK is equal to DN. And we can prove that that's the only line that is equal to DK. Because if it were possible, let another line be equal. Let's call this P. So if it were possible, let dP be equal to dk. Well, if dP is equal to dk, dN is also equal to dk, so two things equal the same thing are equal to each other. Therefore, dP is equal to dk. I'm sorry, to dN. So these are both equal to dk, therefore dP is equal to dN. So this is equal to this. But what's the problem with that? We just proved that as lines get more remote from the one through the center, they get longer. So this, we're saying that this is equal to this, but it also must be greater than this. dP must also be greater than dN. So it can't both be equal to and greater than. And this occurs whether we put it inside or outside, so there's no other line equal to dk except dN. And so since that's the one and only line that's equal, that's the third part of the proof. And so we conclude our proof with QAD.